Lastly, I want to take another look at a system that we've met a couple of times before, and that's the traffic light system. The traffic light system is also a system that goes through a finite sequence of states, but from the point of view of design, it is impractical to implement it using the method that we've seen so far, using a Moore machine. And to see why that's the case, we might just want to try designing it in the simplest possible way. We have the north-south lights, we have the east-west lights, we have a red light, a green light, we have a red light, a yellow light, a green light, a red light, a yellow light, a green light. And if we start with this traffic light with its green light on, then this one had jolly well better have its red light on. After some length of time, we're going to want to take this to yellow to warn us that things are happening. Then we will go to a brief red-red state. Then we will go to this one staying red, but this one becoming green. This one stays red. Becoming green. This one goes yellow. And finally, we're back to red-red. And that's a problem. All of our previous systems have had completely unique states. You've been able to look at the bits that form the state information and know exactly where you were in the diagram. With our traffic light, that's not true. If you see that the traffic light is in the red state, you do not know whether this one is about to become green or this one is about to become green. So for this particular system, we are going to have to do the design in a different way. And one of the other signs that we don't need this much information, that there's redundant information in this system, is that we've got 6 bits to drive these 6 lights. 6 bits can handle 64 possible states, and yet we're only using 6 states. Clearly there must be some simpler way of doing this. So what we can do is to separate the information about the state from the information about which light is turned on and which light is turned off. So if we set about constructing a bubble diagram for this, we're going to need 6 states for our bubble diagram. So I'll start off with my 6 bubbles. And I'm going to put in the middle the numbers from before. So 1, starting with this red light on and this green light on. And then we went, I think I did that backwards. I'm going to start with this green light on and this red light on. Then we'll turn this yellow light on, leaving this red. And we'll go to the first red-red state. Then we'll go to this, the left one being red and the right one being green. Left one is still red, the right one is now yellow, and then finally we've got the other red-red state. So those are what we want the outputs of this system to be. But we don't need 6 bits to encode 6 states. 6 states we can encode in only 3 bits. So I'm going to write up at the top state information, and I'm just going to number the states in order. 010, 001, 010, 011, 100, and 101. And now our traffic light looks like this. It's just a divide by 6 using an internal counter to keep track of which state we are in, but the outputs from it are more complicated. So this means that we have divorced the state information from the output information. So we're going to have to develop this as a different kind of finite state automaton. Instead of taking the outputs from the latches, of which there are only going to be 3, we're going to have to take the outputs from the combinatorial logic. So that's going to produce a different structure for our system. I'm going to still have 3 latches. I'm going to still have a piece of combinatorial logic. My Q's are still going to be inputs to my combinatorial logic. My D's are still going to be outputs from my combinatorial logic. I'm still going to have a common clock that drives everything. So everything so far is the same, but now I'm going to have 6 additional outputs. Red, north, south, yellow, north, south, green, north, south, red, east, west, yellow, east, west, and green, east, west. So my logic is going to be more complicated, and I'm going to be constructing the diagram in a slightly different way. So let's look at how we build the table for this. First part of it is going to be very, very much the same. You're going to need to remember that bubble diagram. First part's going to be very, very much the same. I've got my Q's, which are my inputs, 0, 1, 2, inputs 2, 1, 0. I've got my outputs, D2, D1, D0, O2, O1, O0. I'm using the states 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and 1, 0, 1. And I simply want this to be an up counter. So I just go 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0. So that's just the design for an ordinary up counter. But now I need to also generate the equations for the lights. So I'm going to have 6 outputs. I'm going to have red, north, south, yellow, north, south, green, north, south, red, east, west, yellow, east, west, and green, east, west. And the way we designed this, we wanted the thing to start with this with a green light and this with a red light. Then this goes to a yellow light, leaving this as a red light. This goes to a red light, leaving this as a red light. This will now stay red. And this one will go to a green light, to a yellow light, and back to a red light. And now I can create a larger set of equations. I need my 3 equations for my steering logic, and then I need 6 more equations for the output logic. Some of these are going to be very simple. The green east-west equation is just going to be based on these inputs, so it's just going to be not I2 and I1 and I0. Some of them are going to be a little more complicated because some of them have 4 ones in them. I'm not going to bother to actually write out the set of equations. I just wanted you to see how we would go about designing a system like this, where the outputs come from the logic, not from the registers. And this is, unlike the Moore machine, this machine is called the Mealy arrangement for building a synchronous machine. So with this information, you are now set to go and design your own synchronous machines. And we're particularly good now at designing all kinds of counters, up counters, down counters, counters with external inputs, and that's what's going to be the focus of the lab.